Superposition. If you try to find a real-life example of something that can be in two opposite states at the same time, you probably won't succeed. A light bulb cannot be switched on and switched off simultaneously. Or a window cannot be open and closed at the same time. However, in quantum mechanics it is possible, and the corresponding concept is called superposition. To provide a more formal introduction to superposition in the context of quantum computing, it is first useful to recall the concept of basis states. By definition, a maximal set of linearly independent vectors in the space is called a basis. Linear independence means that the linear combination of all vectors in a set is equal to 0 only if all the coefficients are equal to 0. The simplest and the most common basis is the computational basis, where ket 0 and ket 1 represent either 0 or 1. Superposition is a fundamental property of qubits that makes them different from classical bits. While a classical bit can be in a state 0 or 1, a quantum bit can take any possible value between 0 and 1. In other words, a single qubit can exist in a linear combination of both basis states. Mathematically, a qubit in a superposition can be represented in the following way, where alpha and beta are complex numbers, and alpha squared plus beta squared is equal to 1, ensuring that the probabilities of measuring state 0 and state 1 add up to 1. Complex coefficients alpha and beta are called amplitudes. This state, in other words, when a qubit is in a superposition, can be visualized using the so-called Bloch sphere representation. A Bloch sphere is a representation used in quantum mechanics to visualize the state of a two-level system such as qubit. In the Bloch sphere model, a pure quantum state is represented by a point on the surface of a unit sphere using two coordinates, theta and phi. The north pole of the sphere corresponds to the quantum state ket 0, the ground state. The south pole corresponds to the state 1, the excited state. And points on the equator represent superpositions of these states. The x-axis corresponds to the 0 phase between ket 0 and ket 1, and the y-axis corresponds to the angle phi equal to pi half. The other interesting positions on the Bloch sphere are shown on the screen. So, what about multiple qubit states? When dealing with multiple qubits, the concept of superposition becomes even more powerful. A collection of n classical bits has 2 to the power of n possible states, whereas the state of a quantum system with n qubits can be represented as a superposition of 2 to the power n basis states. This means that a system of qubits can represent much more possible states than the same number of classical bits, and therefore one can encode much more information to the qubits, and qubits have much higher computational power. For example, here are the all possible states of 3 classical bits. A 3-qubit quantum register can exist in any arbitrary superposition of these 9 states. Let's consider a 2-qubit system. Each qubit lives in its own Hilbert space, spanned by the basis vectors. The vector states of the joint Hilbert space, which describes the state of a 2-qubit register, are defined by the Kronecker products of the basis states of the two spaces. For example, when the qubit A is in a state 0 and qubit B in a state 1, will correspond to the state vector shown on the screen. Therefore, a 2-qubit system has 4 computational basis states denoted as 00, 0, 1, 1, 0, and 1, 1. In contrast to two classical bits, which can create only these four possible states of the classical register, 0, 0, 0, 1, 1, 0, and 1, 1, a pair of qubits can also exist in superpositions of these four states. And that is a state vector describing a general state of a two-qubit system. The general state of a k-qubit quantum register can be written as a linear superposition of the basis vectors. Here, a kth are complex numbers, and ket phi are the basis states. So, basically, superposition is a combination of basis states. It is worth noting that the computational basis is not the only orthonormal basis. There are infinitely many. One important example is the so-called Hadamard basis. Now we consider one useful example of a superposition state, a uniform superposition. Uniform superposition is a special case where all basis states have equal amplitudes. For a single qubit, it corresponds to any position in a transversal plane of the Bloch sphere. This means that there is an equal chance of measuring 0 or 1 when the qubit is measured. A uniform superposition of multiple qubits can be created, for example, by applying a Hadamard gate to each qubit. Finally, what's important to remember about the superposition? Superposition is a combination of basis states. It doesn't have a classical equivalent. Classical bits are always in a basis state. One qubit superposition state can be visualized on the Bloch sphere.